Hello again. Right, we're doing the second part of Learning Outcome 5, so it's all contained within the muscle presentation, but just to make each video a tiny bit shorter, I'm going to do sliding filament theory on this one. So it's all related to that, and action potentials and more microscopic detail, rather than the last video was more general muscle fibres and muscle actions. Okay, so in the PowerPoint that I've sent you, you can go on and you can click this heart. This heart will take you through to quite a nice little video that explains the sliding filament theory in a bit of detail. Now, it is very difficult to think of it in detail because we can see these muscles. Now we can see them, we can feel them, and we know how they work. But when you think of something that's so microscopic, it's quite hard to understand. So I'm going to try and put it into real life for you. When we had a look at this work, that we labelled that up here, the one that came out the top here, the muscle fibre, I said wasn't the smallest component of a muscle. So let's have a look. What I'm going to draw here is, hold on a second, let me get a bit closer. Okay, so I'm going to draw one whole muscle, a bundle of muscle fibres. Again, we can revise and say what goes around the whole muscle, what fascia, epimysium, what goes around the outside of this bundle, perimysium, what comes out of here, one muscle fibre, and what surrounds a muscle fibre is an endomysium. So that's where our diagram took us up to. But from here, it's made up of these. And these are called myofibrils. Okay, so each one of those is a myofibril. Myo means muscle, fibril, small fibres. So these are myofibrils, and these under a microscope will have the striations. Okay, it will look like so. Okay, and where the overlap happens here will be the darker stripes. Where there's a bit more space, there'll be the lighter stripes. And myofibrils then are components of muscle fibre, but there are two protein filaments that make up these sections that are under a microscope. And I'm going to write those words down for you. So really, on this bit of paper, we're going to end up with 5 words, the most important words that you need for your exam. So what makes up a myofibril? Actin, and myosin. Okay, these actin and myosin will form these. And I know if you're just looking at this for the first time, this isn't going to mean much to you at all. Hopefully it will in a bit. One whole unit. This is one whole unit from there to there. And that is called a sarcomere. Sarcomere. So I've already got 4 things written on here. They're going to be really important for the exam. A sarcomere is a unit that makes up a myofibril. And within one muscle fibre, there could be thousands of these, all next to each other, thousands of sarcomeres. So there have been questions that in the past that say, what makes up, what shortens when a muscle shortens? And the easy answer is a sarcomere. So myofibrils make up a muscle fibre. Actin and myosin are two protein filaments that make up a myofibril. Actin and myosin. Actin is the thin one. So we'll come on and we'll see a better diagram in a minute rather than my one. But actin is the thin one. Myosin is the thicker filament. And on this diagram, which you've got in your book here, this is the thicker one. But it also contains this. That's a myosin head. So we have myosin and a myosin head. And that head does this. So along each of these strands, you have thousands of these heads doing that. And that is going to pull this fibre. This fibre is the actin. Actin is thin. So it pulls the thin fibre closer and closer. So I normally get my students just to do this and think from your knuckle there to your knuckle there, as I drew on here, it would be that line to that line, and there all your fingers interlacing in between. That's a muscle at rest. Let me click on here, a bit clearer. There we go. Okay, this is a resting muscle. It's overlapped in the middle, but it has the ability to shorten. So when a muscle shortens, it gets shorter, but you can see it's also got wider. But it can't shorten any more than that because it's got to the end. Okay, so that's the overlap. That's what makes the muscle wider and shorter. So that's a muscle contracted. That's a muscle at rest. And if we go to this position here, that is a muscle lengthened. If it goes to here, that would be a muscle tear. So it needs to be some contact in the middle, okay, to allow the action to happen. If you can measure the distance from your knuckles in this one, they're a lot wider, a lot further apart, and they're a lot closer together. So what happens when a muscle shortens? The sarcomere shortens. What happens when a muscle lengthens or stretches? The sarcomere lengthens. Okay, so it can be made quite simple when you think of it like that, but looking at these kind of diagrams and maybe reading a textbook or going on the internet, it does make it quite confusing, I find, or quite hard to understand. So the myosin and the myosin heads, okay, they need energy for this to happen. Okay, they need ATP. ATP is adenosine triphosphate. Adenosine and 3 phosphates. Okay, so the energy takes energy for muscle contraction, and then it will relax. But all of these heads will work slightly different times. They don't all work together to have a contraction and then all relax, because if they all relaxed, the whole muscle would just, there'd be no control over it. So they all work slightly different times. So the myosin heads will form a cross bridge formation. When we talk about cross bridges, we talk about this head attaching to the actin to pull the actin closer together. If we have a look at this diagram, okay, you can think of those as your own knuckles, where this thick green line here is one knuckle, and that's the other knuckle. So the green on this diagram are the actin, and the red are the myosin. You can see the little myosin heads. So that, have to think of the 3 states: stretched or lengthened, at rest or normal muscle tone, and contracted. Okay, and the distance between these 2 green lines is the sarcomere. How many sarcomeres form a muscle? It could be thousands, okay, so they make up one muscle fibre. There's another video for you to click on separately and have a little look at that one as well. Okay, so this is a sarcomere, and we can see the different stripes, the darker areas. So from there to there is a sarcomere. Got another sarcomere, so we've got 2 units altogether. Now, what is a motor unit? This is an actual microscopic image of this black thing coming in. This black thing is a nerve. So the nerve comes in and it will split up into tiny little nerve fibres, and it will go to each one of these. Now this is skeletal muscle fibres. Okay, each one is one fibre. Now you can see an end zone here, 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 here. Okay, each skeletal muscle fibre will be stimulated by a nerve ending. If there was no nerve ending, there'd be no contraction. If there was some kind of injury or damage, there'd be no contraction. One motor unit is one nerve coming in that can stimulate anything from 2 to 2,000 muscle fibres. So quite a big chunky nerve, quite an important nerve coming in, can stimulate up to 2,000 nerve fibres. So if that one if that one nerve, there's some stimulation coming in, 2,000 muscle fibres will contract. So it'll be quite a strong action. Smaller nerves in the body might only go to 2 muscle fibres, and if 2 muscle fibres contract, yeah, you might not actually notice it. Okay, it'll just be a small amount. The thing with nerve fibres or nerves, as they work with muscles, is there is an all or nothing principle. So when a nerve has an impulse that comes into a muscle fibre, if there is enough impulse, it will mean that nerve, the muscle fibre, will contract. It doesn't contract 50%, can't be bothered, let's just do a little bit. If it has a stimulation, it will contract as much as it physically can contract. But what makes the power, what defines how much strength we have or the different kinds of activities we need to do, is how many muscle fibres are contracted at once. So if 1 million skeletal fibres are contracted, it's going to be really, really strong action. If 3 skeletal fibres are contracted, okay, there won't be much at all. So again, this is having a look at it's a bit better image, this one. This is the nerve coming in. So the motor unit. Motor unit is the nerve and the muscle. The one nerve and the fibres that nerve stimulates. Okay, so you've got the nerve fibres coming in. They're the skeletal muscle fibres, and you can see the striations. Each tiny little, I don't know if you can, but each tiny, tiny little line that goes down here is the sarcomere. Motor end plates are where the nerve ends, and that is where the stimulation happens. That's where the impulse will jump across, and we'll look at that, to the muscle fibre to tell the muscle fibre to contract. So this is a neuromuscular junction, NMJ, neuromuscular junction. So from our brain, central nervous system, through our spinal cord, central nervous system, into our peripheral nerves. We'll look at nerves in another PowerPoint. The impulse is going to come down to a nerve ending. So this is a nerve ending. As the impulse comes down, it will tell these little vesicles here that are full of a neurotransmitter. And a neurotransmitter is a chemical that will need to pass across into the muscle fibre to tell the muscle fibre to contract. Now, is it written on here? If I can read backwards. I can't. Let me have a look. Here we go. Can you see that? Acetylcholine. Acetylcholine is a neurotransmitter that will tell the muscle fibres to contract. So the nerve impulse will come down, whether it's conscious or unconscious control, whiz down here, and the neurotransmitter will release this acetylcholine across the junction to be picked up. And down here, can we recognise anything already? Can we recognise which one are the actin fibres? The actin fibres are the blue fibres. The myosin fibres, the ones with the little heads on it, they're the thicker ones. What's that distance from there to there called? Okay, 1 unit that will contract, that's the sarcomere. So when the neurotransmitter is picked up, there will be a contraction. Okay, and it will contract as much as it physically can. potentials. So I've kind of talked about this already, but the resting potential. When a neuron or nerve is at rest, it doesn't send a signal. So there's no release of chemicals. None of these chemicals will pass across into the muscle fibre, and the muscle fibre won't contract. So it'll be at rest. When there's enough impulse and enough surge, and it does get complicated, but we're not going complicated. So when there's enough surge, there will be some chemical passing across to the muscle fibres. And this will cause the muscle fibre to contract. An action potential. Okay, where there's enough impulse, there will be an explosion of activity which will cause the neurotransmitters to pass across the membrane. So all or none, all or nothing principle. The action potential is always the same size. There is no big or small action potential. If there's enough chemical, it will pass across and will tell the muscle fibre to contract. It will contract at a certain rate. Okay, it won't be a huge rate, it won't be a tiny rate, it will be a rate it will contract at, all or nothing. As I said, there's no 50%. If a neuron reaches its threshold, it will fire and cause this action potential. I use an example of going to the fridge. Let's say we've got a 4-pint of milk in there. And you open the fridge door and you put your hand behind, you don't look in, and you left it last night pretty full, nearly 4 pints of milk in there. So you pick it up, but someone in the middle of the night come down and spilt it or drank it or whatever they did with it, and they left a tiny little amount in there. So in this big 4-pint of milk bottle, there's hardly anything in it. But you think there's 4 pints. So your brain has calculated, it's amazing how this happens, it's calculated how many muscle fibres you need to recruit to pick up the amount of weight needed for a 4 pint of milk. So you lift it quite strongly, and because there's nothing in there, your hand hits the top of the fridge. And then you go around the house asking who's drank all the milk and send them to the shop. But that's just demonstrating the fact that your body is calculating this all the time. It's like going down steps and you think there's another step and your body reacts to that, and maybe you trip up at the end. But we are adjusting the amount of muscle fibres we need to do all these different actions. Think of how many muscle fibres needed to pick up 10 kilogram weight. Think of how many muscle fibres are needed to thread a needle and to sew or do something really fine, to hold a little paintbrush. Okay? It will recruit the amount of muscle fibres it needs to do a particular action. It's not the strength of the action, it's the amount of muscle fibres recruited. Okay, so for the sliding filament theory, here's the important bits. We've got the sarcomere, they're the units, thousands of units that you will see as stripes or striations that make up skeletal muscle fibres. There'll be a series of these through the whole muscle. So a sarcomere is a unit. What happens when a muscle shortens? The sarcomere shortens. Myofibrils make up one muscle fibre, and myofibrils are made up of these two protein filaments, actin and myosin. Actin is the thin one, myosin is the thicker one, which contains the heads, the myosin heads, and the heads will form the cross bridges. They're the ones that pull the actin closer. I'm going to write down another word in case you didn't see it. Okay, at the bottom here, acetylcholine. What was acetylcholine? Okay, that is the neurotransmitter. That's the neurotransmitter that goes from the created nerve impulse across the junction to the muscle fibre. So it's a neurotransmitter. And another important thing is this ATP, adenosine triphosphate. Okay, and that's the energy needed for muscle contractions. Okay, so they're all the important words that you need in your exam for sliding filament theory. Okay, go away and have a little learn, have a little revise, have a check out the videos. Go on to Google, go and search for sliding filament theory for children. I find looking at things for children a lot easier to understand, and they explain it really well rather than a bit too complicated. But I hope you know a little bit more than you did before you started watching this. Okay, all right, thank you.